guys, so in this video we're going to cover expressions with radicals and rational exponents. So first I want to just review some exponential properties. So we have the product rule, which just says that if you have the same base and you're multiplying those things together, then you add the exponents. The quotient rule is very similar, but it's when you're dividing. If you're dividing same base, then you subtract the exponents. So with multiplying same base, you add the exponents. Dividing same base, you subtract the exponents. Now, the power rule is when you have a power next to a power. So you have something that has a power, and then you have a power on top of that. You would multiply the powers together. And then the power of a product just means that if you have multiple things multiplying together, or even dividing, the power of a quotient also works. So if you have one term, things either multiplying together or dividing, then you distribute that power to all of the things. So every number, and if there's a coefficient, to the coefficient, and also to every variable as well. So you can see here in this example, we have 3xy squared, all raised in parentheses to the power of 4. So that's 3 to the power of 4, x to the power of 4, and then y squared to the power of 4. And so because that's a power of a power, you would multiply them together. So you end up with 81x to the 4th power, y to the 8th power. Now, one thing that is very common to make, so I wanted to point this out. Do not make this mistake, okay? 3x squared is not the same thing as 3x all squared. So the 3x squared, the squared's only going to the x, okay? Whereas 3x squared, the squared is going to both the 3 and the x. So this would be 9x squared, okay? Now, what about a negative exponent? Well, whenever you have a power that is negative, you can just change the side of the fraction that that base is on, and it becomes, or not that it becomes, but then it will change to a positive. So, for example, here I have 3xy raised to the negative 4th power over z raised to the negative 2 power. Now again, if we look at this over here, right, the 2 is only for the x. Here, that negative 4 power is only for the y variable. So you're going to move the y to the negative 4th power to the denominator, and then it becomes a y to the positive 4th power. Then in the denominator, we have z to the negative 2 power, so we could change that to a z to the positive 2 power, bringing that to the numerator. So it just changes the side of the fraction that it's on. If it's a numerator, it becomes the denominator, and vice versa. Now the zero rules. Anything raised to the power of 0 is 1. Excuse me. And 0 to the power of anything is 0. And that's for positive values only, because let's say we had a negative power, right? Let's say it was 0 to the power of negative 1. Well, technically, then that would be, put that numerator as a denominator, 0 to the power of 1, and then so technically you're dividing by 0, which is undefined in math. We cannot do that, right? So that is why the power, when the base is 0, has to be positive. Now, what about 1 rules? Well, anything to the power of 1 is itself, right? So a to the power of 1 is just a. And 1 to the power of anything is 1, no matter what it is. And then the negative 1 rule, I included this one as well. If you have a negative and it's raised to some power, right, then you have, you're multiplying that amount of copies. So if you have an even number of copies, then that'll end up being a positive number because you have an even amount of negatives. Negative times a negative is a positive. So when you have an even amount of negatives multiplied together, that'll end up being a positive, versus when you have an odd number of negatives, you're going to end up with a negative. And that's all this says. So negative 1 raised to an even power will give you positive 1, and negative 1 raised to a odd power will give you negative 1. Okay, so let's just do some examples with simplifying just as a review, okay? So remember with simplifying, you're gonna want to use whatever exponential properties, right? All of these exponential properties that we know. And then each base at your ending answer can only be occurring once. So if you have like x squared y z over x, that's not simplified because you have that that base of x showing up more than once. So each base can only occur once in order for it to actually be simplified. Then no negative exponents. This means that if you have your final answer, and let's say it was x y over z to the power of -2, well, that's not simplified because you cannot have any negative exponents when it's being simplified either. Okay. So let's take a look at this one. The first thing that I always do is I distribute any power of a power. So here we have x to the power of 2 to the power of 3, so this will be 2 times 3, and then y to the power of 4 to the power of 3, so that would be 4 times 3. We also have just times 3 and then times x to the power of 4 and a times y to the power of -5. Now let me go ahead and simplify this a little bit further by multiplying this out. So 2 times 3 is 6 and 4 times 3 is 12. So now we have x to the power of 6, y to the power of 12, and I'm just going to bring this 3 to the front. Usually we always write any numbers in the front for our coefficient. And then we also have x to the power of 4 and y to the power of -5. Now, you could bring this to the denominator as the y to the positive power of 5, but I also see here that I have the same base, right? So I can actually add those exponents because we are multiplying these bases. Also, I have multiple bases of x, so I can add those exponents as well. So this will end up being 3 times x to the power of 6 plus 4, which is 10, times y to the power of 12 plus -5, which is 7. Okay. Let's do the next one. So, and again, just remember, once you're done, if you only have bases occurring once and you have no negative exponents, you're good to go. So now I'm going to go ahead and look at number 2. So we can distribute that power of 4 to each one of those, right? Power of a power. So I'm going to multiply and distribute that to each thing. Y to the power of 3 times 4. And then in the denominator, we have 4 times x to the power of 0. I'll actually just simplify that right now. Anything to the power of 0 is 1. And then y to the power of -5. Okay. Now I'm going to go in. 2 to the power of 4 is 2 times 2 times 2 times 2. 2 times 2 is 4. 2 times 2 is 4. 4 times 4 is 16. Or you could use a calculator, of course, but that was easy to do. And then x to the power of 4, y to the power of 3 times 4 is 12. And then in the denominator, 4 times 1, of course, is 4, and then y to the power of -5. Now, I see multiple bases with the y, right? So I have y to the power of 12, and I have y to the power of -5. Now, this is dividing, right? So if you're dividing, because we have a fraction, same base, then you subtract the exponents, top minus bottom, okay? So we have 16 divided by 4, which is 4, of course. And then, like I mentioned, 12 minus -5 will be 12 plus 5. So I have y to the power of 17. And so in the denominator, I just have 1. So in other words, our final answer is 4x to the power of 4, y to the power of 17. All right. Moving right along, let's take a look at number 3. So for number 3, we have a lot going on. Again, just do this a little bit at a time, okay? So first start with the power of a power. I suggest that always, just because you can simplify that a little bit further, right? So I'm going to distribute that power to all of the different numbers and variables inside. So 2 to the power of -2, x to the power of -10, y to the power of 6, times 3 times x to the power of 3 times y. In the denominator, we have 3 to the power of -1, X to the power of 0 again will just be 1. So multiplying anything times 1 would just be the same, so I'll just disregard that. And y to the power of 12. Okay, now that we've simplified this a little bit, I'm going to go in and simplify this a little bit more. What I'm actually going to do in this case, and this is something that I could have even done here, is I'm going to move all of the things that have a negative power to the opposite side, okay? And that's going to help me out a little bit to simplify this a little bit further. So I'm going to bring 2 to the power negative 2, x to the power of 10 to the bottom. So 2 to the positive power of 2, x to the positive power of 10. Then I'm going to move the 3 to the power negative 1, which is on the bottom. I'm going to move that to the top, 3 to the power of positive 1. Everything else has a positive power, so I'm just going to leave it where it's at. So all of these stay on the numerator. Now, when I'm writing this out, 3 to the power of 1, I'll write first. Since it's a number, I'll end up multiplying that with the other 3. And then y to the power of 6 and y to the power of 1, obviously these are in the same numerator, so they're multiplying together. So we'll add the exponents. Y to the power of 6 plus 1 is 7. And then x to the power of 3. In the denominator, we have that y to the power of 12, so I'll leave that right there. Okay, now we're going to go ahead and multiply. 3 times 3 is 9, and 2 to the power of 2 is 2 copies of 2 multiplied together, so that's 4. And I have multiple bases, okay, with y and multiple bases with x. Now, another tip that you can do, I can do 7 minus 12, which will give me negative 5. So that would be y to the power negative 5 in the numerator. And I could do x to the power 3 minus 10, which is negative 7, and that would be x to the power negative 7 in the numerator. But what I like to do when I have multiple bases, another tip that you could use is canceling out the copies. So you have 7 copies in the numerator that can cancel with 7 copies in the denominator, which will give you a total of 5 copies in the denominator. Then we have 3 copies of x in the numerator, which would cancel out with 3 copies of x in the denominator, leaving 7 copies of x in the denominator. So overall, we end up with 7 copies of x in the denominator and 5 copies of y in the denominator. So our final answer, and 9 over 4 doesn't simplify, but if it would, obviously you would simplify that. Numerator is 9, denominator is 4x to the power 7, y to the power 5. Now, normally when we have variables in the denominator, we do want to state if we have any excluded values, okay? And I'm just going to fix this 7. That looked a little funky. Still not very good. Let me try that one more time. 7, there we go. We have to state whatever value that variable cannot be, because then it would make the denominator 0. So x cannot be 0, and the variable y cannot be 0 either, because if either one of those variables was 0, then we would have 0 in the denominator, and that is undefined. All right, so go ahead and pause this video now and try number 4 on your own. All right, so let's go over number 4. So we have 3 x squared y to the power 5, all raised to the power negative 3. So this would be 3 to the power negative 3, x to the power of 2 times negative 3, and y to the power of 5 times negative 3. In the denominator, we have 9, x to the power negative 4, and y to the power of 7. Okay. Right from here, we can simplify some of these powers that need to be multiplied together. So 3 to the power negative 3, x to the power of 2 times negative 3 would be negative 6, and y to the power of 5 times negative 3 would be negative 15. Okay, and in the next step, I'll kind of mimic what I did in the previous problem, is I will move anything that has a negative power to the opposite side. So I'm going to move actually all 3 of these to the denominator. So 3 to the power of 3, in the denominator x to the power of 6, in the denominator y to the power of 15 in the denominator. And I'm also going to move x to the power negative 4, which is in the denominator that has a negative power, to the numerator. Now, 9 and 7 were both in the denominator and had a positive power, so that'll stay in the denominator. I'll put the 9 in the front because I'll need to multiply that with 3 to the power of 3 eventually. And y to the power of 7, of course. Now, 3 to the power of 3 is 3 times 3 times 3, which is 27. And 27 times 9 is, let me just verify, 27 times 9 is 243. Okay. Now the next thing that I want to do is I see multiple bases, right? I have multiple bases with x and I have multiple bases with y. So because these factors are on top and on bottom, I can cancel out 4 copies of x on top with 4 copies of x on bottom, leaving 2 copies of x on bottom. And then both of these copies of y are in the denominator. So I'm going to use the product rule. These bases are multiplying together, and I'm going to add the powers. So in the denominator, I have x to the power of 2 and y to the power of 15 plus 7, which is 22. Okay, very interesting. All right, now in the numerator, right, we canceled out all of our different things, right? So really we just have a 1 there that remains. And that is the answer for number 4. All right, let's move on to some radical rules, okay? So these radical rules, some of them you already should know. For example, the root of a product, right, is where you have a radical and you have multiplying things on the inside of that radical. You can split up that multiplication. So if I have, for example, the cube root of 2x squared y, well, 2 is multiplying with x squared, which is multiplying with y. So you could split all that up. Cube root of 2 times cube root of x squared times cube root of y. Another one that you should already know is you could do the same thing with division, right? So if I have the nth root of something that is being divided, I could split up that division, nth root of the numerator divided by nth root of the denominator. So for example, if I have the 4th root of 3x over y cubed, I could split that up and write it as the 4th root of 3x over the 4th root of y cubed. Of course, I could also split it up using the product rule here. Since 3 and x are multiplying, I could split that up into the 4th root of 3 times the 4th root of x all over the 4th root of y cubed. Now, I wanted to point this out because I do not want you to make these mistakes, okay? You cannot do the same thing with addition and subtraction, okay? You cannot split up the roots when you're adding or subtracting. All right. And another common mistake that is made is thinking that the power will cancel with addition or subtraction. So the power here does not cancel with the root. Because a lot of times you say, oh, well, x squared square root is x. Yeah, but that's just one term, right? If I had the square root of x squared plus y squared, that does not equal x plus y. Okay? All right. So, the one rule that is completely new to us in this radical rule table is the fractional exponent. And this is the one that this lesson really covers. So we have x to the power of m divided by n. So that's when you have a fraction, which is rational is another fancy way to say fraction, right? When you have a exponent that is rational, when you have an exponent that is a fraction. Now what happens? The denominator of that fraction, power, is actually the root. Okay, so for example, if I have x to the power of 3 over 4, x to the power of 3, of course, is x to the power of 3, but the division of 4 in that exponent actually gives us or tells us that it's the 4th root. So the numerator would stay with the base, but the denominator is where we get the root piece from. So we're going to be simplifying these examples And let's start with A. Okay, so we're going to just be using these rules. And the rules, of course, that we covered before with exponential rules, which you should already know. So write an equivalent expression for each of the following expressions. Okay, so what I like to do with these is first just write it all out with putting the power onto it, right? Now, some of these you will already know, like the cube root of 27 I know is 3, because 3 times 3 times 3 is 27. So it's kind of a mixture of putting the denominator onto the power, and also if there are numbers, you could figure out whatever that is. You can also use a calculator for that. So cube root of 27 is 3, and then a to the power of 3, and then we have the root of 3, which is the denominator. And then the fourth root of 16 is, of course, 4. Actually, no, 2. I was thinking square root. The fourth root of 16 would be 2, because 2 times 2 times 2 times 2 is 16. So 2 to the power of 4 equals 16. So the fourth root of 16 is 2. And then b to the power of 8. And then the radical is 4. That's the index. So that goes in the denominator of the exponent. Okay. So now we have 3 times 2, which is 6. A to the power of 3 divided by 3, which is 1. And b to the power of 8 divided by 4, which is 2. So our final answer is 6ab squared. All right. Let's look at b. All right. So again, you want to find the fourth root of 81. All right. Now, I'll use a calculator for this one because for some reason I'm not remembering what the fourth root of 81 is. Is it 4 times 4 times? No, that's 64, I think. No, that's way too big. I don't think 81 is a... Let's try... No, because 3, well, let's try 3. 3 divided by 3 divided by 3 divided by, oh, it's actually 3. 3 to the power of 4 is 81. Okay, so the fourth root of 81 is 3, and then x to the power of 2, and then the root goes in the denominator of the fraction. Y to the power of 5, and then again, the root goes in the denominator of the fraction. Okay, now 2/4 obviously we can simplify to 1/2. Okay, and y to the power of 5/4. Okay, that is a mixed number. Now, some books keep it like that. This would be the answer. And some books will split this up, because 5/4 is 1 whole and 1/4. So you can take out the 1 full copy of y. So you could write it as x to the power of 1/2 y to the power of 1/4, because it is 1 and 1/4. Now, I personally don't think that we should write it like this, because then you have multiple bases, which defeats the whole purpose of making sure that you have only one base. But depending on, like on the SAT, you might see it like this or like this, but they would never give you both answer choices as like which one is correct. You would see one or the other, but there's 2 ways to write it. You can either write it like that, or if it's a improper fraction, you write it as the mixed number. The whole number is how many whole copies you have, 1 whole copy of y, and then the fraction is what remains. And you can split it up that way. All right, let's look at C next. And actually, before I continue, let's talk about how these are using rational exponent. So this is if you were going to keep it with rational exponents. But you could also write it as radicals, okay? So if you were to write it as radical, you would keep that power and then put the radical with the index of whatever the denominator is. So you keep the power for the base, whatever's in the numerator, and then the denominator, that's what goes in the index for the radical. So that's when you're writing it as a radical, you do need to 100% split it up like this because you are simplifying the radical. So for example, you would have a whole copy of 3y, but then you have a square root of x to the power of 1. And it's a square root because the denominator is 2 for that power, for that base of x. And here we would have y to the power of 1 to the 4th root because the denominator is 4. So it is actually important to be able to split this up this way if you have to write it as a radical. You have to take out any full copies that you have. That's like having the square root of 8 and leaving it like that. Well, the square root of 8, that's not correct to leave it like that because we have, 2 to the power. The square root of 8, first off, is 2 to the power of 3, right? But we have 2 full copies of 2 there. So you have to bring that out. It would be 2 square root of 2, right? So it's the same idea. If you have a full copies in a radical that can come out, you have to bring them out. So all 3 of these ways could be considered correct. It just depends on what the question asks you for. Both of these are technically correct if you are asked to write it with rational exponents. But if they ask you to write it with radicals, then you definitely have to make sure that you split up how many full copies you have, and then you write it, the power of the numerator stays with the base, and the denominator is what the index is for your radical. So let's move on to C. Okay, now notice that this radical doesn't have any index, so obviously it's the square root. And I have a numerator and denominator. So the first thing I'm going to do is I'm just going to split it up. 4x to the power of 4 all over the square root of 256y to the power of 8. Now, all of this is being raised to the power of -2, okay? And you know what? I just realized that that power is negative. So let me take back a step and move that to the numerator because it's going to get a little bit confusing if I don't simplify that on the inside first. So I'm going to move that to the numerator. It's all raised to the power of -2. So I'm just going to move the whole thing raised to the power of +2. And that means that there would be nothing left in the denominator, which is why I didn't, keep any fraction there. Now, that power of 2 would then distribute to both of these. And I could simplify this first, or I could go ahead and distribute the power, every single thing having divided by 2 in the power for this radical. I'm going to go with the route of, let's simplify first, because I have a lot of things going on right now, and usually when there's a lot of things going on, I like to simplify first. So let's distribute that power of 2 to both. 256 raised to the power of 2 be 256 times 256, which is 65,000. That's a lot. 536. Okay, and then y to the power of 8 to the power of 2, of course, 8 times 2 would be 16. So I have x to the power of 4, y to the power of 16. All right. I can also then multiply the 65,536 times 4 is 262,144. And of course, x to the power of 4, y to the power of 16. So the square root of 262,144, I'm going to try and see if that is a perfect square. And it is. Wow. Okay. So the square root of this number is 512. And then x to the power of 4, again, denominator is the index 2. Y to the power of 16, denominator is the index 2. 4 divided by 2 is, of course, 2. 16 divided by 2 is 8. And then we bring down the coefficient, which is 512. And that's all, folks. Let's look at D and E very quickly. So for D, let's just inside switch. Actually, no, because we're distributing a power of -5 anyway. So let's just distribute the power of -5. And here we're using power of a power, right? So I'm going to multiply -5 times -5, y to the power -3 times -5, and even that it's all in parentheses, so it goes to the denominator as well, z to the power 3 times -5. So -5 times -5 is 25, -3 times -5 is 15, and 3 times -5 is -15. So now I have positive powers in the numerator, but this one is a negative power. So I'm going to move that to a positive power, bringing that to the top. So we have x to the power 25, y to the power 15, z to the power 15. And that is our final answer. All right, last one, E. Now, this one can be a little tricky if you were thinking like, oh, well, the variables, blah, blah, blah. But if you think about what is the rule, it's actually really quite easy. So first, let's do the 4 divided by 2 part, right? That's easy. That's just 2. And then now we're looking at the base of y, okay? Now, when you have the same base and there's division, what do you do with the powers? You subtract them, right? So I'm just going to take the power in the numerator, and that gets subtracted with the power in the denominator. So we end up with 3x minus 2, which is minus 2x, which is 1x, and -3 minus positive 4, which is -7. So our final answer is 2 times y to the power of x minus 7. All right, go ahead and pause this video now and try number 2 on your own. Okay, so hopefully you were able to work these ones out. And let's start with part A, right? So we are doing the 5th root of all of this stuff inside, all right? Now, if you're thinking, well, root of a negative, no, that's imaginary, right? Remember, only even roots of negatives. So like if I had the square root of -1, yeah, that's I. But the cube root of -1 is just -1, because -1 times -1 times -1, or in other words, -1 to the power of 3, is actually -1. Versus this has to be I, because there are no numbers that when we take that base and we put that to the even power, it gives us a -1. What? No, right? So that's why we needed imaginaries when we have even roots. But with odd roots, no problem. Okay, so the 5th root of -32 is... So I'll actually show you how to enter this on the calculator because it is the 5th root and not like just the square root. So you should be familiar with this button. You hit second and you hit this button, and then that's how you get the square root, right? Square root of 4 is 2. Okay, great. How you do any other power or any other index, I guess, is first you have to write whatever the index is. So we're doing the fifth root, so we'll put a 5. And then you hit the second button, and this is the one that we want to get to, some random index radical. So that's the button that we press, and then so we can do the fifth root of negative 32, and it'll give us that is negative 2. Okay, that's also the button that you can do for any random power. So like you could press this button for this squared, right? 4 squared is 16, but you can press this button, the up arrow, to put any power. 4 to the power of 5 is 1024. So both of these buttons, this one's just power of 2 and square root, and then this is any power and any root. So the fifth root of negative 32 is negative 2. And then we can write x to the power of 10, and then fifth root, so divided by 5, y to the power of 5, fifth root, so divided by 5. And then times the cube root of 8 would be 2, and x to the power of 21, which is the third root, so divided by 3, and then y to the power of 6 divided by 3 as well. So let's simplify this. Negative 2 times 2 will be negative 4. X to the power of 10 divided by 5 is 2, and 5 divided by 5 is 1. 21 divided by 3 is 7, and 6 divided by 3 is 2. Now we do have multiple bases, so we are going to have to consolidate these guys together. So y to the power of 1 and y to the power of 2. We have to get together as well. So x to the power of 2 times x to the power of 7 will be x to the power of 2 plus 7, which is 9. Y to the power of 1 times y to the power of 2 will be y to the power of 1 plus 2, which is 3. And that's our final answer for part A. Let's move on to part B. So in part B, we have a fraction. Now, I would highly suggest just simplify what's inside here first and then worry about distributing the cube root, right? So let's move this from the denominator to the numerator. So we have the cube root of the numerator, 27x to the power 9, times, and then I'm just, the whole thing, it's in parentheses, 216 z to the power of 6, it's raised to the power of negative 3, so I'm going to move it to the numerator, raised to the power of positive 3. Now I can go in and distribute that power of positive 3 to both of those, so we end up with the cube root of 27x to the power of 9, and then 216 to the power of 3. Oh, wow, large number. 1,007,7696. Okay, and then z to the power of 6 to the power of 3 is power of 18. All right, and then 27 times that large number is cube root of 272097792. Okay. And then, of course, we have, I just did those two multiply together. We still have x to the power 9 and z to the power of 18. Now, I need to find the cube root of this, and I'll actually show you on the calculator. Let me just clear everything. I'll show you what you can do, because on your calculator, right, you would have already have done all of the calculations. So you would already have this number in your calculator, right? You got that as a result with the last calculation that you did 27 times that. Now, there is a quicker way that you could do the cube root of that. So we're going to do cube root, right? And then normally right here, we would just start typing in the number 27209, blah, blah, blah. And that's quick and whatnot. But you can actually, if you have, if what you're trying to take the root of is the thing that you had previous, you can hit the second button and then click this button right here, the negative, because on top of it, you see it says ans. That's short for answer. So it'll just replace with ans. It'll replace whatever the answer was from the previous calculation that you just made. So this will do the cube root of this number. And it's just a quicker way so you don't have to type it all in again. So we end up with 648. All right, that worked out really nicely. It's a whole number. And then x to the power of 9 it's the cube root of x to the power 9, so it'll be x to the power 9 divided by 3. And then the cube root of z to the power of 18 will be z to the power of 18 divided by 3. So final answer would be 648. X to the power of 9 divided by 3, which is 3, and z to the power of 18 divided by 3, which is 6. And that is our final answer for part B. Moving right along, let's look at C. Okay, so we have a lot of negative powers. You know, what I'll do right now is just move the negative powers to the opposite side. So I'm going to move these two terms to the denominator, and I'm going to move these two terms to the numerator. So 6 to the power of positive 1, b to the power of positive 3, 3 to the power of positive 2, a to the power of positive 5. And then a to the power of 2 will stay in the numerator because that was positive. B to the power of 2 will stay in the denominator because that was positive. Now, 3 to the power of 2 is 9, so we'll simplify that. Also, these two are multiplying together. 5 times 2, a to the power of 5 times a to the power of 2 will be a to the power of 5 plus 2, which is 7. And then in the denominator we have 6. B to the power of 3 times b to the power of 2 will be b to the power of 3 plus 2, which is 5. And then 9 divided by 6, of course, I can simplify. Divide 3 on top and bottom. 9 divided by 3 is 3. 6 divided by 3 is 2. So we end up with our final answer, 3a to the power of 7 over 2b to the power of 5. And again, we do have a variable in the denominator, so we do want to mention that b cannot equal 0. All right, last one, part D. So for part D, we have that same exponent where we have an expression, right? So first, let's just simplify the numerator. We have that same base of a, right? A raised to some power. But we're multiplying these bases, right? So when you multiply bases, what do you do with the exponents? You add them. So I'm going to do a to the power of 3b plus 2 plus 2b. And then, of course, the denominator, I'll just leave this alone for now. Okay, let's simplify that. 3b plus 2b is 5b. So now I have a to the power of 5b plus 2. Over a to the power of negative 2b minus 5. Okay, now we still have that same base of a, right? If the bottom base was something else, then I would be done. But we still have multiple bases of a, so I need to consolidate those. When I'm dividing same base, I subtract the exponents. So I will do the exponent on top, 5b plus 2, minus the exponent on bottom, which is negative 2b minus 5. So I will now just go ahead and simplify that power. 5b minus negative 2b will be 5b plus 2b, which is 7b. And positive 2 minus negative 5 would be positive 2 plus 5, which is positive 7. And that is the final answer. All right, guys, so I hope that that was helpful, and I will see you guys in the next video. Bye.